This lecture is part 2 of Section 3.5 from Math 311 course in linear algebra at Western Illinois University. We're continuing to wade our way through this very lengthy, important section on subspaces, basis, dimension, and rank. So in the previous video, we talked about what a subspace is. Remember, a subspace is a set of vectors which includes 0 and is closed under vector addition and scalar multiplication. Today, in this lecture, we're going to start by talking of some more subspaces that are associated with a matrix. And in fact, there are three subspaces, at least three subspaces that are associated with any arbitrary m by n matrix A. And they're right here. The first is called the row space of A, and that's just the span of the rows of A. The column space of A is the span of the columns of A. And the null, we have something called the null space, which is denoted by null A, and it's basically the set of all vectors, all column vectors V, such that A times V is the 0 vector. Okay. Another way of thinking about this is that this sort of corresponds to all the solutions of a homogeneous linear system represented by A. So we have actually found the null space of a matrix many times. We just didn't know we were actually doing it. The row space and column spaces, because they're the spans of a finite set of vectors, they're automatically subspaces, right? All right, because you know, this is because all spans are subspaces. Okay, the only difference is, the only detail here is that here this is a subspace of Rn, because there are n columns in this matrix, so the rows have n entries, and the columns have m entries because there are m rows in this. So there's that to consider. And now we're just going to prove that the null space is in fact a subspace of Rn. So remember the three things we need to check. We need to check that the zero vector is in here. So clearly 0 is going to be in the null space, since I think we can agree that A times 0 is 0. Okay. Then if, let's say, U and V are in the null space of A, then A times U equals 0, and A times V is equal to 0. So A times U plus B, we need to show that that is 0, and by the distributive law of matrices, this is AU plus AV, which is 0 plus 0, which is 0. Okay, so U plus V is in the null space. And then if C is any real number, we need to show that CU is in the null space. So A times CU, we need to show that's 0, but we can do that real quickly because C is a scalar. We can pull that out in front. So this is C times the 0 vector, which is 0. So CU is in the null space. Okay. And thus, the null space of A is a subspace. Okay. So if let's look at an example of all three of these subspaces. Here we have this, on page 2, we have this relatively nice matrix, and it's nice because it's in, you might notice that it's in reduced row echelon form. And I picked this up because, well, things are easier when they're in reduced row echelon form, and turns out that's what we can, ultimately what we want to do is, reduce a matrix to reduced row echelon form. So in this case, we can see that there are 3 rows. Okay, so I think we can clearly see, hopefully we can clearly see that the row space of A is just a span of 1, 0, 2, 0, 0, 1, negative 3, 0, and 0, 0, 0, 1. Right? And this is obviously in R4. This is a subspace of R4. The column space of A consists of the columns, right? So this is a span of 1, 0, 0, 0, 1, 0, 2, negative 3, 0, and 0, 0, 1. Okay? Now it's a perfectly good spanning set, but I think you can see that this third vector here is a little redundant, because we can write this as we can write this as 2 times 1, 0, 0 plus negative 3 times 2 times 0, 1, 0, right? So this vector can be written as a linear combination of these. So as a result, we can actually just write this as the span. You can basically remove this. This is not necessary, because any linear combination of these will be a linear combination of these 3. So this is going to be the span of 1, 0, 0, 0, 1, 0, and 0, 0, 1. And in fact, this is just all of R3. Okay, so that's column space. And then we're going to see that notice that this set, these 3 vectors are linearly independent, whereas these are linearly dependent, because this can be written as a linear combination of the others. And that's kind of a big deal, but it will be a big deal on the next video. Okay. The spanning set, remember, the spanning set of a subspace is not unique. Just okay. Then what's the null space of A? Okay. Well, to do this, we need to sort of remind ourselves. Well, how do we find the null? How do we find the solution of a homogeneous linear equation? You have, these are basically your A is basically representing what we're trying to do is we want to find what's it called, x1, x2, x3, x4, and we want this to be equal to 0, 0, 0, 0. Okay, so basically we're trying to find all quadruplets that such that this is true. Well, what this basically means is that 1 x1 plus 0 x2 plus 2 x3 plus 0 x4 equals 0. Then we get 1 x2 minus 3 x3 plus 0 equals 0. And then 0 plus 0 plus 0, 1 times x4 equals 0. All right? So this is going, so what are we talking about here? We are going, we can see that we sort of have a free variable here corresponding to this column at this x3. Everything can be written as x3, because x1 can be written as minus 2x3, x2 can be written as 3 times x3, x3 can be written as x3, and x4 is 0. Okay, so we can see that the null space of A is just the span of the vectors negative 2, 3, 1, and 0. Okay. All right, because this is really equal to x3 times negative 2, 3, 1, 0. Okay. Right. And again, you can write this, just leave your answer like this. There's really no other option, right? Because there are infinitely many vectors in the span. You can't write them all out, so you just give the spanning set. Okay. Okay, a couple things here. Notice that there are three, the span of the row space. We can get a spanning set where both we can choose our spanning vector so that the row space of A is spanned by 3 vectors, and the column space is spanned by 3 vectors. Okay, that's going to be no accident. In fact, we can always arrange it so that the row space and column space are spanned by the same number of vectors, even if one space is contained in R4 and the other is contained in R3. Another thing we'll see is that the spanning set of the null space and the spanning set of the column spaces, they equal to the total number of columns, and that basically corresponds to the fact that we had 1, 2, 3 pivot columns in this matrix and 1 non-pivot column, and that corresponds to the free variable, right? In this basically, because essentially what we were doing is we were doing solving a homogeneous system. So, before we just wrote this as this. Okay, and we could do reduced row echelon form, and we could get the same answer as we got here. So really, finding the null space isn't that much different than what we've done previously. We just have a different notation for it. Okay, now, as I said before, reduced row echelon form is very, very helpful to us, and right now we're going to see why. So we're going to see more evidence why. So on the next page, the whole idea here is we want to show that if we perform elementary row operations on a matrix, it does not change the row space. And so and also it doesn't change the null space either. So just to prove why this is, or give a sketch of a proof, remember what are the 3 kinds of elementary row operations that you can perform on the rows. You could interchange 2 rows, you could multiply 1 row by a non-zero constant, and then you could add a multiple of 1 row to another row. And what we want to show is that none of those operations change the row space of the matrix, because obviously in this first case, this is the span of any of a set of vectors is equal to the span of any permutation of those vectors. It really doesn't matter how you order them, right? In a case, let's say, where you just have V1 and V2, any linear combination of V1 and V2 is also a linear combination of V2 and V1. We just rearrange the order, right, which we can do with addition. Next one is if we multiply 1 vector by a non-zero constant C, that doesn't change the span either. And the way we want to check to show these spans are the same is we need to show that every linear combination over here is also a linear combination over here, and vice versa, right? So any linear combination in the span of the V's will look like this. And then for the VI term, we can basically multiply and divide by C, which we can because C is not 0. We can rewrite this term as A sub I divided by C times C. Okay, and then use parentheses here. And what we have is a linear combination of these vectors. Similarly, if we take a linear combination of these vectors, we'll get something like this. And once again, we can just group our parentheses, and then because A times C is just a number, we get a linear combination of the V's, the linear combination of our original set. So this span is the same. Also, if we take if we replace, in this case, if we replace VI with VI plus C times Vj, where I is not equal to j, we'll get that these spans are the same, because any linear combination of this first set we can rewrite by basically adding and subtracting AI C times Vj here, and then breaking them up, and then this is going to be, this term becomes something times Vi plus CVJ plus something times VJ. Okay, and VJ is already in the set of the is already in this set somewhere. So so any linear combination of the V's any linear combination of the first set is equal to the linear combination of the second set, and similarly any linear combination of the second set will be a linear combination of the first set, because all we have to do is just basically break this up. This is AI times VI plus AIC times VJ, and so everything here is a linear combination of the original V's. Okay, so these spans are the same. Okay, so what we've shown is that if we take if these VI's are rows of a matrix, okay, we can see that the row space will be unchanged by any particular for any one elementary row operation. Okay, or another way of saying this is that if we for any elementary matrix E, we have the row space of EA is the same as the row space of A, because remember EA is just A with the elementary row operation that E represents applied to it. Okay, so so if we do one elementary row operation doesn't change anything, then two operations won't change anything either, right? Because we can just multiply this by another elementary row matrix, and then that would leave the row space unchanged. So we get number 5 is that if B is a matrix that's obtained from A by a series of elementary row operations, then the row space of B is equal to the row space of A. And we should say that the technical term for this is we say that A and B are row equivalent. Okay, that's just saying that one matrix can be obtained from the other by a series of elementary row operations. So the elementary row operations don't change the row space. By the way, I should say that that's not true with column spaces. Okay, so Warding, I should say Warding, in general, in this case, the column space of B is not equal to the column space of A. Okay, in general. All right, but in this case, that because every matrix has a reduced row echelon form, okay, and reduced row echelon form is obtained by elementary row operations, we get that the row space of A is equal to the row space of its reduced row echelon form, which is great. So in general, if I give you a matrix and I ask you to find the reduced row echelon form, then you just go ahead and if I ask you for the row space and column space and the null space, you want to find the reduced row echelon form, because we can just find the reduced row echelon form and just basically write out the rows of that, and that will be the span the row space. Then you can do the thing we did in our previous example and find the null space. To find the column space, it's a little tricky, but not much, and we'll get into that in the next lecture. But right now, the row space of A is equal to the row space of its reduced row echelon form. And as a consequence of this, we get that if A is an invertible matrix, then the null space is 0, and the row space is all of Rn. Now, the reason for that is, if you remember from last time, by the fundamental theorem of invertible matrices, okay, which we talked about last time, where we said if a matrix is invertible, then it's equivalent to these 4 other things. And one of those 4 other things was that its reduced row echelon form was the identity, and also that the solution to AX equals 0 only has a trivial solution. So if A is invertible, we get first that the reduced row echelon form of A is equal to the identity. Well, remember, the identity just consists of, we have, 1, 0, 0, and 0, 1, 0, 0, 0, 1, and they will all always, we can see that these vectors will span, any element in Rn will be a linear combination of these rows, right? Because, for example, ABC can be written as A times 1, 0, 0, plus B, 0, 1, 0, plus C times 0, 0, 1. Okay. So anything in the row space is really all of Rn. So, yeah. Right, because the span of Rn is just these rows. We also get that if A is invertible, that AX equals 0 has only the trivial solution, and that implies that the null space of A is just 0. Okay, we talked about that last time too. All right, so now actually we're going to see that these three conditions here are not only, we proved that if A is invertible, it implies this and implies this. We're actually going to see that this implies these two, and this implies these two. In fact, all three of these are equivalent, and we're going to sort of fold that into the new version of this fundamental theorem of invertible matrices. Okay, so that's coming. That's coming next. Okay, so all right, so we'll have some more examples of this next time.